I just posted a new worksheet on Canvas. This one's called Newton's second law with friction and slopes. The first problem returns to the scenario of pulling a box across the floor with a rope. This time we're pulling the box at an angle and there's friction between the box and the floor. So here's what the scenario looks like. There's the floor, there's the box, tie a rope around the box, and we pull this thing. That rope makes a 15-degree angle with respect to the horizontal, and there is friction between the box and the floor. So the tension force has a value of 350 newtons. The box has a mass of 120 kilograms, and the coefficient of kinetic friction between the box and the floor is 0.2. So let's draw the free body diagram. Standard horizontal vertical coordinate system. The box is our object of interest. We have gravity of the earth on the box. We've got the normal force of the floor on the box. You've got the tension force of the rope on the box, and there's also the friction force. Remember, friction always opposes the direction of motion, so friction force will be pointing to the left in the negative x direction. Friction force of the floor on the box. Because tension is not lined up with on the axes, we need to find its components. We did this in an example a few days ago. There's the angle. So we have the x component of tension is adjacent to that angle. So it gets cosine. And the y component of the tension force is opposite to the 15-degree angle. So it gets sine. Now we can do our Newton's second law procedure. And when we have these friction problems, remember we need to figure out the normal force in order to figure out the friction force. So that means that first we should analyze the y direction. Some of the forces in the y direction will equal 0 because this box is not moving up or down. And we've got the normal force in positive y. We have that upward component of tension. And we've got the gravity force in negative y. So that means that the normal force equals W minus Ty, or when we substitute mg for W, which is always true on Earth, and substitute this expression, T sine 15 degrees for the y component of tension, now we have an expression for the normal force. So now let's go to the x direction. In x, you've got the x component of tension pulling to the right, and you've got the friction force pointing to the left. Now, friction equals the coefficient of friction times normal force, mu times n. And we can substitute our x component of tension, t cosine 15. And we'll substitute the expression we just found for the normal force in here, mg minus t sine 15 degrees. And with one step of algebra, we've now reached our answer. When you plug in these numbers, you get 1.01 meters per second squared. And if you go back to the other examples we did for this similar scenario where there was no friction, you can see that this acceleration is a lot less. Now I want to point something out about this final expression that we got. This might look kind of complicated. We're starting to get into more advanced problems where your final answer has a lot more variables in it. These expressions can be pretty long. But I just want to point out that you can look at this as saying it's just Newton's second law. It's saying that the acceleration of the system equals the total force divided by mass. A equals F over m. That's Newton's second law. So all this stuff in the numerator is the total force. This first term is how much force was pulling to the right from the rope. That's the x component of the tension force. And this thing right here is the amount of friction force that's slowing the system down. It's mu times n. We had this slightly complicated expression for normal force that we got from analyzing the y direction. But all this is really saying is that the acceleration of this box is the amount you're pulling to the right minus the amount that friction is slowing you down all over the box's mass.